Welcome to the Economist in Your Ear podcast. Have you ever stopped to consider how much of the universe quietly, relentlessly streams right through you, completely unnoticed in the blink of an eye? Because hundreds of trillions of tiny, elusive particles are doing just that every single second. Today, we're zeroing in on the Juno observatory in China, a monumental scientific endeavor that just switched on. It's not just a big construction project, it's a serious contender to unravel one of the biggest, most persistent mysteries in fundamental physics, the very nature of neutrinos.
It really is a fascinating moment in science because Juno, well, it isn't simply designed to spot these invisible particles. Its true mission is to precisely measure their fundamental properties, and in doing so, it could, profoundly reshape our understanding of the universe at its most basic level. The narrative around these big projects often focuses on the awe-inspiring scale, the engineering marvels. But what we're really going to explore today is the more nuanced and often challenging reality behind this scientific quest, looking beyond the headlines, really, to the critical details that truly matter.
Okay, let's start with these particles themselves, neutrinos. They're elementary particles, sometimes called like shrapnel, from nuclear reactions, from the sun, from power plants.
That's a good way to put it. Shrapnel is right.
Yeah.
And they are everywhere.
And elusive doesn't quite cover it, does it? I mean, incredibly light, no electric charge. They basically just goes through everything.
Exactly. Billions of them are zipping through you, me, the Earth, everything right now. And they almost never interact.
It's almost rude.
Well, their elusiveness, that very property, is what makes them such a huge mystery and a profound challenge for physics, because here's the core problem. Neutrinos, they represent a major contradiction for the standard model of particle physics.
The standard model, okay, that's our best theory for, well, everything fundamental, right? Particles, force.
Yeah, precisely. It's incredibly successful. But famously, it predicts that neutrinos should have no mass at all, zero. And yet, observations have clearly, unequivocally shown that they do have mass. It's tiny, minuscule, but it's there. This wasn't just, a small tweak. It was a seismic shock. It told us our most successful theory was incomplete, fundamentally flawed, at least regarding neutrinos.
Right. A huge crack in our basic understanding.
Yeah.
Where did we first start seeing the evidence for this? How did we find out they had mass?
It really started to emerge, about 30 years back now. Two key experiments. First, you had Super Kamiokande in Japan. They noticed fewer muon-type neutrinos coming up through the Earth than they expected based on those coming down from the atmosphere. Something was happening to them on the journey.
Missing neutrinos.
Kind of, yeah. And then, around the same time, the Sudbury Neutrino Observatory, SNO, in Canada, was looking at neutrinos from the sun. They found fewer electron-type neutrinos than theories predicted should be produced by the sun's fusion reactions. These two results, put together, led to this groundbreaking conclusion: neutrinos must be oscillating.
Oscillating? You mean like changing identity, like shapeshifters?
Exactly. That's a perfect analogy. They transform from one flavor, electron, muon, or tau, into another flavor as they travel along. Think of it like a chameleon changing color. And the crucial point, the physics behind it, is that this transformation, this oscillation, is only possible if they possess mass. Without mass, they couldn't change. So discovering oscillation was discovering mass. It was monumental. It immediately pointed to physics beyond the standard model. It told us there's something deeper, something we haven't figured out yet.
Okay, so that sets the stage for Juno, this incredible facility in China. Describe this place. It sounds extraordinary.
It really is. Imagine taking this special yellow train, and it just plunges down this steep tunnel, deep underground, for 10 minutes.
10 minutes down.
Yeah, deep beneath Dashi Hill in southern China. You end up in this gigantic cavern, like an underground cathedral, really, over half a kilometer of rock above you. And right there, in the middle, is this enormous sphere, steel and plexiglass, 12 stories high.
12 stories. Well,
inside that sphere, 20,000 tons of this special liquid, a liquid scintillator. It's designed to give off a tiny flash of blue light when, just occasionally, a neutrino bumps into one of its atoms. And lining the inside of that sphere are 40,000 incredibly sensitive light detectors, photomultiplier tubes, waiting to catch those faint flashes.
And its main job is counting neutrinos from power plants.
That's right. 2 nuclear power plants about 53 kilometers away. The 700 meters of granite overhead acts like a shield, blocking out other distracting particles, cosmic rays, and so on, so they can focus on the neutrinos. The sheer scale is just, mind-boggling, all for these tiny, tiny particles.
So how does counting these reactor neutrinos help solve the next big mystery? You mentioned mass ordering.
Right, the mass ordering or mass hierarchy. So we know neutrinos have mass, and we know they oscillate between flavors. But it gets a bit more complicated. Each neutrino flavor, electron, muon, tau, isn't actually a single mass. It's a quantum mix, a superposition of three underlying mass states. Let's call them V1, V2, and V3. As a neutrino travels, the way these three mass states are mixed changes slightly, and that's what causes the flavor change, the oscillation.
Okay, a mix of three masses.
Exactly. Now, the question is, how are these masses ordered? Is it what we call normal ordering, where V1 is the lightest, then V2, and V3 is much heavier? Or is it inverted ordering, where V3 is actually the lightest, and V1 and V2 are the heavier ones? Current data kind of leans towards normal ordering, but it's not decisive. There's still wiggle room.
And Juno can tell the difference.
How? That's the goal. By precisely measuring the energy of the thousands of neutrinos arriving from the reactors. There are very subtle differences in the energy pattern, the spectrum, depending on whether the ordering is normal or inverted. It's incredibly subtle. They expect maybe 50 detections a day. So over about 6 years, they hope to gather around 100,000 neutrino events. Enough, hopefully, to see that subtle difference and make a definitive call.
50 a day. Aiming for 100,000. It sounds like a clear plan. But, science, especially at this scale, it's never quite that simple, is it?
Yeah.
Our background material really highlights some significant challenges, some scientific caveats. This is where it gets really interesting, I think. What hurdles does Juno face?
Absolutely, and that's crucial context. We need to talk about the scientist's caution here. How sure can we be? One of the biggest challenges is controlling what are called systematics. These are tiny, unavoidable uncertainties in the experiment itself. Things like knowing the exact temperature of that huge volume of liquid scintillator, or understanding precisely how the neutrino output from the reactors might fluctuate slightly over time. Juno needs to control its energy measurements to an incredibly fine degree. We're talking sub-percent precision. That's almost unbelievably difficult.
Okay.
Without that level of control, the subtle difference between normal and inverted ordering could get lost in the noise, in the uncertainty. The results wouldn't be definitive. And that 6 years timeline, it's plausible, yes, but it's certainly not guaranteed. Things like calibrating the detector perfectly, making sure you understand and subtract all the background noise from things like natural radioactivity in the rock or stray cosmic rays that sneak through. That all takes time, often more time than initially planned. It's just the reality of doing this kind of precision neutrino physics. It's painstaking.
So given these challenges, these systematics, how much confidence can we place in Juno's result alone? Does it need backup?
That's a really important point, and the answer is yes, collaboration is key. Juno isn't working in a vacuum. It's actually one crucial piece of a much bigger international effort. And what's really exciting is that scientists plan to do combined analyses. They'll combine Juno's data with results from other major experiments, like KM3 Torca, which looks for neutrinos coming through the Earth under the Mediterranean Sea. These other experiments use different techniques, look at neutrinos from different sources, like the atmosphere.
So different angles on the same problem.
Exactly. Juno's reactor approach is complementary. And you've also got Hyperkamiokande coming online in Japan, hopefully around 2027, and the DUNA experiment in the US, maybe early 2030s. When you have different methods, different experiments, all pointing towards the same answer, that's when you get really robust physics. It helps beat down those systematic uncertainties. The combined picture is much stronger than any single result.
Okay, so the main goal is the mass ordering. But it sounds like Juno can do more than just that. It has other tricks up its sleeve.
Oh, absolutely. Its capabilities go well beyond just particle physics. There are some really significant, let's call them payoffs in other fields that maybe don't get as much press. For instance, Juno is set to become the world's best detector of geoneutrinos.
Geoneutrinos. Neutrinos from the Earth itself.
Yeah, from the natural radioactive decay of elements like uranium and thorium deep inside the Earth. Juno's sheer size and sensitivity mean it will detect hundreds of these every year, far more than ever before. For geologists, this is gold. It's like giving them an X-ray of the Earth's interior. It helps them figure out how much of the Earth's internal heat comes from radioactivity versus, say, leftover heat from when the planet formed. It constrains models of mantle convection, the engine-driving plate tectonics. It's fundamental Earth science.
Wow, an X-ray of the planet. That's incredible. What else?
Another really cool application is supernovae, exploding stars. Juno is joining a network called SNU WS 2.0, the Supernova Early Warning System. See, when a massive star collapses and explodes, it releases an enormous burst of neutrinos before the visible light reaches us, maybe hours, potentially even days before.
So it's like an advance warning.
Exactly. Juno, along with other detectors in the SNU-WS network, could detect that neutrino burst. That gives astronomers precious time to point all their telescopes, optical, radio, X-ray, at the right patch of sky before the explosion becomes visible, to catch it right from the very beginning. There's even talk of potentially detecting neutrinos from a star before it goes supernova, giving an even earlier heads up.
Okay, this is all fascinating. Let's circle back to the particle physics, though. You mentioned inverted ordering versus normal ordering. I read somewhere that theorists find the inverted ordering possibility more exciting. Why is that?
That's right. There's generally more buzz among theorists about inverted ordering. Although, honestly, any definitive answer from Juno will be huge news in constrained theories. But inverted ordering, if it turns out to be true, well, it opens up some really profound possibilities more immediately. It hints strongly that there might be new physics just around the corner, as they say. Specifically, it makes it much more likely that we could experimentally test whether neutrinos are their own antiparticles.
Their own antiparticles, like photons.
Exactly like photons. Most particles have distinct antiparticles. Electrons have positrons, protons have antiprotons. But some particles, like the photon, are their own antiparticle. Maybe neutrinos are like that too. We call particles like that Majorana particles. Theories that explain the neutrino's tiny mass, like the seesaw mechanism, often predict neutrinos should be Majorana particles.
The seesaw mechanism, yeah. That's the idea that neutrinos are light because they're linked to some incredibly heavy, unseen partner particles.
That's the basic idea, yes. Like balancing a seesaw, if one side is extremely heavy, the other side can be extremely light. And getting back to your earlier point, some versions of this theory even suggest those super heavy partner neutrinos could potentially be candidates for dark matter, the mysterious stuff that makes up most of the universe's mass.
So how would we test if neutrinos are their own antiparticles? And how does the ordering tie in?
We'd look for an incredibly rare type of radioactive decay called neutrinoless double beta decay. Normally, in double beta decay, an atomic nucleus spits out 2 electrons and 2 antineutrinos. But if neutrinos are their own antiparticles, Majorana particles, then very, very rarely, the 2 antineutrinos could essentially annihilate each other inside the nucleus, and the decay would happen with only the 2 electrons coming out. No neutrinos or antineutrinos detected.
Okay, so you look for this specific decay signature.
Exactly. And here's the link to Juno's mission. The predicted rate of this neutrinoless decay depends directly on the neutrino masses, and specifically on the ordering. If the ordering is inverted, the calculation suggests this decay should be happening just often enough that the next generation of supersensitive experiments like LEGEND or NEXT might actually detect it in the next 10 or 15 years. Finding that would be revolutionary. Confirmation of Majorana neutrinos, strong support for the seesaw mechanism, potential links to dark matter. It would open up whole new avenues in physics.
But if Juno finds normal ordering...
If it's normal ordering, the predicted rate for neutrinoless double beta decay is likely much, much lower. Probably too low to be seen by any experiment we currently know how to build. It wouldn't rule it out completely, but it would push the possibility much further away. So you can see why inverted ordering feels like it might unlock new doors sooner.
Right. So Juno isn't just measuring a number, it's potentially pointing the way towards a whole new understanding of fundamental particles, and maybe even the cosmos itself.
It absolutely is. That's why its switch on is such a big deal. It's a genuine, ambitious step forward, not just for the mass ordering, crucial as that is, but also as this unique, powerful tool for looking inside the Earth and catching exploding stars. It's about this global collaboration, too. So the things to watch for are practical milestones. Can they achieve that incredible energy or precision they need? When do we see the first results on the reactive neutrino spectrum? What did the first geoneutrino measurements tell us? And maybe most importantly, how did Juno's findings line up with results from KM3Net, Hyper-K, and eventually DUNE? If Juno delivers, the next few years could really trade a lot of speculation for solid data, pushing us towards a much more complete picture of the universe.
The journey to understand the universe's smallest, most elusive particles is a testament to global scientific collaboration and the painstaking pursuit of precision. Juno, with its blend of ambitious goals and meticulous methodology, reminds us that the biggest mysteries often hide in the quietest corners, patiently waiting to reveal their secrets. And perhaps the most profound secret it could uncover isn't just how the universe works, but whether you are fundamentally made of matter that had an antimatter twin. Thanks for listening. Follow us to stay updated with the latest insights on The Economist every day, And don't forget to like, comment, and share.